Hello, I'm Andrew Aubin from Waters Corporation, and I'd like to speak to you today about the development of a strategy for scaling SFC methods, applications for preparative chromatography. Scaling methods in liquid chromatography is well established and well understood. Unfortunately, the same cannot be said for scaling methods in supercritical fluid chromatography. In this presentation, I'd like to discuss some of the things that make scaling in SFC challenging and some of the factors that influence scaling success in supercritical fluid chromatography. In supercritical fluid chromatography, the density of the carbon dioxide mobile phase significantly influences the separation. Therefore, changes in the methodology, whether they be flow rate or particle size or other factors, can significantly change the separation. These are the factors that make scaling challenging. You can see in figure 1 an example of a particle size change with identical chromatographic conditions. Looking at this chromatography, we can see, although the conditions are identical, the chromatography is significantly different. This is functionally because the density of the carbon dioxide in these two separations was different. So if we want to do scaling accurately and precisely, we need to control the density between these two separations. So how do we do this? First thing we have to do is understand what's going on the column. When running columns of two different particle sizes, the average density within those two columns is going to be different. Because those densities are different, chromatography is different. So we need to come up with a way to make that average density, which is really average pressure, the same. If we can make the average density the same across these two different columns, we can make our chromatography look exactly the same, as can be seen in the next set of figures. We can further illustrate this process by modifying flow rate. Of course, as you know, if we modify flow rate, that will modify pressure, that will modify density. If we apply the same principle of keeping our average pressure the same across our column, even when we start changing flow rates, we can keep our chromatography very similar. That's in the next figure. If we were to do this in liquid chromatography, it would be very predictable and work every time without any changes to the method. In SFC, we do have to modify the pressure parameter to keep our carbon dioxide density the same. So what does this mean in a practical example? We want to scale chromatography from analytical to preparative to conserve sample, to conserve solvents, to conserve time. When we start applying these techniques to scaling from analytical to preparative and keeping our density constant, it allows us to develop this chromatography analytically and scale it to preparative chromatography without making significant changes to our preparative method. We can also start to consider length of column and particle size together. In liquid chromatography, using L over dP, that's length divided by particle size, we can accurately predict how long of a preparative column we will need relative to the size of the analytical column. The same calculations can be used in supercritical fluid chromatography as long as the average density is taken into account. If we use L over dP as part of our calculations and include the density calculation as well, we can start to make our chromatography moving from small particle, short analytical columns to large diameter, long preparative columns, allowing us to make our chromatography very similar. From a practical perspective, this works very well for isocratic chromatography. Turns out that it also can be applied to gradient chromatography as well. It is slightly more challenging because as you run your gradient, pressure does in fact change, therefore density changes. Still, if we take an average pressure, we can apply these same techniques to gradient separations and have very similar chromatography. This allows our workflow to go from analytical to preparative without major manipulations of the preparative chromatographic separation method. In conclusion, taking a systematic approach, taking into account some of the variables in supercritical fluid chromatography that don't exist in liquid chromatography, it is quite straightforward to be able to scale from analytical to preparative, from one diameter column to another diameter column, to use smaller particle columns on analytical separations to larger particle columns on preparative separations. This average pressure approach has proven itself to be useful when changing column IDs, lengths, flow rates, and particle sizes. Well, the data here was shown only using standards. The next steps in this process are to use real-world samples and real-world workflows. Thank you for your attention.